Okay, sorry guys. I just noticed that when I was recording my video, the bottom and top edge for the slides are cut. So when I was writing some equations at the bottom of the slides, perhaps you don't see it. So I just reset my settings, and then I'll show you the slides one more time. So here, if temperature of C equals to temperature of A, and meanwhile temperature C equals to temperature B, then temperature A should equals temperature B. That means the A and B, they're in thermodynamics. Actually, they're in equilibrium of thermodynamics. So this is called thermal equilibrium, and this is the zeroth law of thermodynamics. Okay, next, temperature scales. So in daily life, there are two different types of commonly used temperature scales. For example, the Celsius and Fahrenheit temperatures. So for Celsius degrees or Celsius temperatures, they are commonly used in some countries like UK or some Asian countries. But for Fahrenheit temperatures, it's more commonly used in US and some other countries. They can be converted into each other, and they have a linear relationship. It's very easy to convert that if you have an equation. So here it shows the equation of converting the temperatures. Okay, so let me convert my pen into laser point. Okay. So this is the equation of converting a Celsius temperature into Fahrenheit temperature. And in another way, you can also convert it back from a Fahrenheit temperature into Celsius temperature. So what's the difference between Celsius temperature and Fahrenheit temperature? So in Celsius temperature scale, 0 degree is the freezing point of water, and 100 degree is the boiling point of water. Fahrenheit temperature, 32 degree is the freezing point of water, and 12 degrees is its boiling point. So that's the difference between Celsius and Fahrenheit temperatures. And another concept is absolute zero temperature. So 0 degrees in let me convert it back into a pen. Okay, so what happens? So 0 degrees in Celsius temperature doesn't mean it's absolute 0 degrees. Because if we do an experiment, we will understand that 0 degree is not real absolute 0 degree. Do remember we explained the energy in previous preparation lectures? Now let me show it one more time. Do you remember these slides we have learned before? This is the thermal energy of objects. So why does object have thermal energy, or why does object has a temperature? So simply because the molecules in the object, it has energies, and if you sum all of those energies up, then you get thermal energy of the object. Then that is the thermal energy, and that is related to the temperature. If the temperature is higher, that means the thermal energy of this object is higher. So here is microscopic of the thermal energy or temperature. So in an object, the molecules are moving. So if the kinetic energy of molecules are higher and the potential energies are higher, then the average energy of each molecule in the object is higher. Then in a microscopic way, you'll get a high temperature object. In another way, if the kinetic energy of molecules, for example, in the ice, okay, let me convert it into, okay, it's not in slides, so I cannot convert it into pen, but at least you can see my cursor. So if you see the cursor here, for the ice, the molecules in the ice, they're not moving as fast as in the hot iron, and they're not vibrate as much as in the hot iron. Then the kinetic energy and the potential energy for the molecules in the iron is lower. That's a microscopic vision. In the microscopic vision, that means low temperature. So what about if all the ions are not if all the molecules are not moving at all? So all of them are at their equilibrium position and they don't move at all. Then that will be the absolute zero temperature. Means there's no energy in the molecules at all. However, even for ice, if you zoom in enough into the molecules, the ice molecules, you will see even for ice, the molecules are still moving and they're not restricted at the equilibrium states. So they still have kinetic energy and potential energy. So this is not real 0 degree or zero temperature. By doing some experiments, people use some gas to try to find out what is zero or absolute zero temperature. If you put some gas in a container, you can measure the pressure from the gas to the wall of the container, and you will see the pressure will decrease when the temperature is decreased. So for example, each line is different type of gas. Let's use a pen here. Now let's see this line. If this line, at this point, you have some high temperature, so the pressure is also high. If you lower the temperature to 0 Celsius degree, you will feel you will measure the pressure of the gas is lower, and if you lower the temperature into even low degrees, the pressure will also get lower. So it's getting lower and lower, and finally you can reach a point at which the pressure is 0. Of course, experimentally, it's impossible to get this point. However, after several measurements, you can get some points like here, here, here. If you connect them into a line, you will see it's a straight line. And finally, you can predict when this line reaches the point, that will be the absolute 0 degree. By using different type of gas, for example, this is number 1 type of gas, this is another type of gas, this is the third type of gas. Using different type of gases, you will find actually they're pointing the same temperature, which is negative 200 73.15 degrees in Celsius degree. That's the absolute temperature, absolute zero temperature. If in a way you can reach this temperature, then your object will have no energy at all. It doesn't contain, all the molecules in the object, they won't have any kinetic energy, none, and no potential energy. So that's zero, absolute 0 degree. Okay. So due to the absolute 0 degree, we define another type of temperature scale, which is Kelvin temperature scale. In Kelvin temperature scale, 0K is the temperature that the gas has no pressure, or it's the absolute 0 degree. So to convert Celsius degree into Kelvin degree, it's very easy. So Tk equals Tc just plus 273.15. And of course, you can convert Tc, you can convert Tk into Tc. Okay. Now, here are some temperature conversions. So if you know the equations here and here, and also this equation, if you know all the 3 equations, you can convert any temperature scale into the other 2 temperature scales. For example, you can convert K to C or F, something like that. So here are some comparisons between 3 temperature scales. Okay. So thermal expansion. So as you know, when an object is in a high temperature situation, the volume of this object will be expanded. This is called the thermal expansion. That means increasing the temperature of a rod or any other object will cause it to expand. For moderate changes in temperature, the change in length is given by this equation. So, for example, if you have a rod with original length to be L0 at temperature T0, if you increase the temperature by delta T, now you have T0 plus delta T degrees, then your length of the rod will be increased by delta L. And if your temperature is increased by 2 times delta T, then the length will be expanded by 2 times delta L. So how to calculate this delta L? After many experiments, people find a way to do a calculation of this expansion, delta L, which is shown here. This is delta L, or change in length, and alpha is coefficient of linear expansion. So it depends on different material. So L0, which is original length, delta T, it's a temperature change. So different material will have different alpha, or different coefficients of linear expansion. Some material are very easy to be expanded by temperature, while others are not. So it's completely depends on material. So now let's explain why an object will increase in size when the temperature is higher. So let's get back to the microscopic of an object. So for example, this is an object. Inside an object, you will see a lot of molecules. and molecules, they have interactions with each other. It's like springs connecting the molecules. When the temperature is higher, the spring between two molecules will increase. So any spring between any two neighboring molecules will increase by some size. So when the length of the springs are increased by temperatures, then on the microscopic view, you will see the object is increased in size. Okay, so that's the mechanism behind this thermal expansion. Okay, here is a molecular basis of thermal expansion. Here is a graph showing the minimal and maximal lengths of let's say the atoms, the distance between atoms. Let's go back to the spring model. Let's see if you have two molecules, 1 and 2. They are connected by a spring. Actually, when temperature is increasing, the distance between molecule 1 and 2 is changed in this way. So, for example, when the temperature is higher, or when the energy is getting higher from E1 to E2, the minimum distance between the two molecules is changed from some high or longer distance into a shorter distance. And the maximum distance between those two molecules is increased from a lower value to a higher value. See, this is getting longer. But if we consider about the middle point between the minimum distance and max distance in low energy and high energy, you will see the middle point is shifted to be a longer distance. And when the energy increases, the middle point is increased more. So the middle point is increased little by little. That means the equilibrium states or length of between the two molecules is increased little by little when the energy is increased. When the thermal energy is increased, means when the temperature is increased. That's why when temperature is increased, the spring is getting longer and your object is getting bigger. So it's quite interesting that, let's say, if you have let's say a square with a hole inside, and when the temperature is getting higher, or if the object is getting hotter, actually the hole inside is also getting bigger. So this is a quite interesting phenomenon. It doesn't shrink, instead it's getting bigger. So the whole size of the square is getting bigger, and the hole inside the square is also getting bigger. So let's see the volume expansion. We have learned that the length of object expands when temperature is getting higher, and the volume of the object is also getting bigger when the temperature is getting higher. And the equation is given here. The delta V, or the change of the volume of the object, equals to B V0 delta T. and B is the coefficient, actually beta is the coefficient of volume expansion, which is 3 times alpha. And alpha is given in this equation, which is coefficient of linear expansion. Okay, so this is the way of calculating the volume expansion. Here you have some coefficients of linear expansions. There's a list. For example, for aluminum, the coefficient is higher. For brass, it's a little bit lower. For copper, it's lower. And you see, for steel, actually, it also has a high value. So, generally speaking, for metals, most of the metals, they have high value of alpha, or they're easy to be expanded when temperature is getting higher. So this is the coefficient of volume expansion. As we said, it's just 3 times of alpha. So for example, this is 2.4 for aluminum. If you use 2.4 times 3, then you will have 7.2. So again, most of the, the metals, they get high value of the coefficient of expansion. Means when you're using some metals, they're very easy to be expanded when temperature is getting higher. That's why, for example, on the roadway, the railroad track always has a gap between segments here to allow for thermal expansion. Because in summer, when the temperature is very high, the railroad track, they grows in size. So the length will increase. You have to have some gap to avoid the buckles. Okay. An interesting phenomenon is that between 0 degree and 4 degrees in Celsius degrees, the water decreases in volume with increasing temperature. So here, this is a graph of volume versus temperature. So usually if you look at the general line, you'll see for water, when the temperature is getting higher, the tendency of the volume is getting higher. However, if you zoom in into this small area, you will notice that actually it's about here. Actually, between 0 and 4 degrees, if you zoom in enough, you will see the temperature, when the temperature is getting higher, the volume is getting lower from 0 to 4 degrees. This is only for water. Why water is so different from any other material? It's quite a complicated problem. It's related to the hydrogen bond and other factors. But let's remember that from 0 to 4 degrees, when the temperature is increasing, the volume of the water actually is decreasing. And that's why lakes freeze from the top down inside instead of from the bottom up. Because let's say when the temperature is getting lower and lower, the volume of water need to be increased. So the easiest part to increase volume of a lake is the top water. So the top water is easy to increase in size. So that's why the lakes freeze from top, because their volume are easy to be increased at the top. And another concept is the thermal drift. If we change the temperature of a rod but prevent prevent it from expanding or contracting, the thermal stress develops. This is thermal stress. So the thermal stress could be calculated using this equation. So here, F is the force needed to keep the length of rod constant. A is the cross-section area of the rod, equals to negative y alpha delta t. Y is Young's modulus. This Young's modulus depends on material. If you have different materials, this modulus value is different. So alpha is the same thing, the coefficient of linear expansion, and temperature is as a delta T is a temperature change. Okay, so similarly, on bridges, you will have expansion joints on the bridge, which are always needed to accommodate the changes in length, which is from the thermal expansion. Okay, next, quantity of heat. Sir James Drew studied how water can be warmed by vigorous stirring with a paddle wheel. So for example, if you do some work to the water by just stirring a paddle wheel, you let this paddle rotate round by round, and then finally you will feel when it's rotating, it's doing some work, and the temperature of the water will be increased. So that means if you do some work, you can increase the temperature of an object. Another way to increase the temperature is by putting the water in contact with some hotter body. For example, if you set up a fire here and you try to use a high temperature fire to heat the water, the temperature of the water can also be increased. So this is the two ways of increase temperatures of water. The first way is doing some work to the water. The second way is just putting the water in contact with some hotter body. Because when the water is in contact with the hotter body, there's some heat transferred from the hotter body to water. This is the definition of heat. So the calorie means the amount of heat required to raise the temperature of 1 gram of water from 14.5 degree into 15.5 degree. This is a definition of 1 calorie, and its abbreviation is CAL. So this is a very commonly used daily unit for heat or work. Okay. The quantity of heat requires to increase the temperature of a mass m of a certain material by delta T is given in this equation. So Q equals to mc delta T. Q is the heat required to change the temperature of a certain mass. M is a mass. C is specific heat of material. It depends on types of material. Delta T is a temperature change. So the specific heat C has different value for different materials, and the specific heat of water is about 4100 joules per kilogram K. But actually, this specific heat is not very commonly used. Instead, another commonly used quantity is the capital C, which is molar heat capacity of material. So the quantity of the heat Q required to increase the temperature of n moles of a certain material by delta T is given by this equation. So this is the heat. N is a mole heat capacity of material. And N is the number of moles of material. And delta T is the temperature change. So this is the equation when you calculate the heat required to increase the temperature of n moles of the material. And the molar heat capacity C has different values for different materials. And for water, the molar heat capacity is 75 joules per mole times K. Here are some values for the molar heat capacity C or specific heat C here. So we can see for water, let's see, where's water? So for water, it has a relatively big value compared to other materials. So that means if you want to heat up water by the same delta T or the same change of temperature, it's more difficult. Let's compare water and let's say copper. See, the value of copper is very low. That means if you want heat let's say 1 kilogram of copper by 1 degree, it needs much less heat than you heat up the water in 1 kilogram by 1 degree. So water is difficult to heat. Okay, next, phase change. So for the same object or same matter, it might in different phases. So for example, the most commonly phases are solid, liquid, and gas. For example, we all know the water has 3 phases. Solid means ice, liquid means liquid water, gas, and we commonly see those 3 types of phases for water in daily life. And for other materials, they might also have the 3 phases. A phase change is a transition from one phase to another. The temperature does not change during a phase change. For example, if you have some ice which are melting, so when the ice is melting, you will have less and less ice, more and more water. But when it's melting, the temperature is always 0 degree, unless all the ices are transferred into water. And then if you heat the water again, the temperature of water will be changed. However, during the phase change, for example, if you have a container, there's some ice and water. If they're in the equilibrium, if they're in the thermal equilibrium, then the temperature has to be 0. Even you heat them, or if you try to lower if you try to absorb heat from the mixer, from the ice water mixture, the temperature doesn't change. It's always 0 degree, unless all the ice are converted into water, or all the water are converted into ice. So latent heat, L, is a heat per unit mass that is transferred in a phase change. So here is a heat transfer in a phase change. It equals to mL. So m is the mass of material. L is latent heat for this phase change. So Here is a figure of the temperature change when the water is undergoing the phase changes. Let's say at the lowest temperature, -25. Um, if we try to heat up the water, or actually at this temperature the water is ice. If we try to heat up the ice, the temperature of the ice will be increased little by little, and then it reaches 0 degree here. Once it's 0 degree, the ice starts to melt. Then the ice is undergoing a phase transfer. It's transferred from ice to liquid water. So that's a mixture of water and ice. And then even you continue to heat up the ice and water mixture, then the temperature doesn't change. It's always 0 until all the ices are transferred into water. And then if you continue to heat up the water, the temperature will get higher. And then it reaches the 100 degree. Another type of phase transfer happened. So this phase transfer or phase change is from liquid to gas, or liquid water vaporizes, and this temperature is 100 degree. If you keep heating up the system, more and more liquid water will be changed into steam or gas phase of the water. So you keep heating up the system, but the temperature will not change. It's always 100 degree until all of the liquid water is converted into steam or gas water. And then if you keep to heat up the system, the temperature of gas will increase. That's the entire process of heating up the ice into water and then into steam. Okay, so heat up fusion. So for example, when you heat up the ice will melt. The similar thing is happening to other material. For example, for the metal, if you heat up the metal and get the temperature high enough, the metal will melt or will be in fusion. For example, the metal gallium, which is shown in this picture, melting in a person's hand because it's one of the few elements that melt at room temperature. Its melting temperature is 29.8 degrees, and its heat of fusion is 8 times 10 to the power 4 joule per kilogram. That's why even if it touches your skin, it will melt, because your temperature, the body temperature, is higher than this temperature. Then it melts. And the heat of vaporization. So when some material is undergoing vaporization, it will take some heat away. So the water may be warm and it may be a hot day, but if some kids get out of some swimming pool, they will feel cold because when water evaporates from their skin, it removes the heat of vaporization from their bodies. To stay warm, it's better for them to dry off immediately. Otherwise, when the water on their skin try to evaporate, then it take off some heat. They will feel cold. Okay, so another topic is a heat transfer. In nature, there are three ways of transferring heat. They are called conduction, convection, and radiation. So conduction occurs when a hotter body is contacting in a colder body. Then uh, the heat will conduct. The heat conduction will happen, and the heat flows from a hotter object to colder objects. Convection depends on motion of mass from one region of space to another region of space. Radiation is the heat transfer by electromagnetic radiation, such as sunshine, and um, sometimes some other rays. It also radiates the heat from one object to another. So now first let's see the details about the conduction of heat. In conduction, the heat flows from a higher to a lower temperature object. For example, if you have two objects here and here, you have a high temperature object and a low temperature object, and if they're contacting each other, or if they're contacting the same object, then the heat will flow from one object to another one. The left end of the rod is kept as a temperature Th, and the right is in a lower temperature Tc. The rate that the heat is transferred can be calculated in this way. So we use H, stand for heat current, and it equals to dq over dt. That means the rate or the ratio of the heat flow. It equals to Ka delta T L. So Th is a high temperature, Tc is a low temperature. So Th subtracted by Tc is delta T. K is thermal conductivity of rod material. A is cross-section area of the rod. L is the length of rod. So from here, we can see the rate of heat flow depends on several factors. If we want to keep the rate of heat flow in a big number or big value, so perhaps first we want some thermal conductivity, a high value material. For example, metal. So metal has a high thermal conductivity. So that's why when we make some let's say pot for cooking, usually they're made by metal because they have high value of thermal conductivity. And again, if the cross-section area of the rod is bigger, then the rate of heat flow is greater. And if the temperature difference is greater, then the rate of flow is greater. When the length is shorter, then this rate of heat flow is greater. So that's the equation of calculating the rate of heat flow. Here gives some values for different types of material for their thermal conductivity. So for example, silver and copper and aluminum, actually all the metals, they have relatively high value of thermal conductivity. That's why we use metals for the cooking ware. Okay, so here is a convection of heat. Okay, so here is a picture of putting the high temperature and metal into the water. You will see if you put it into water, you will see it's producing a complex pattern of free convection. This is called heat convection. This is another way of transferring heat. The last type of transferring heat is radiation. So here is a radiation map, or it's a false color infrared photograph to reveal the radiation emitted by various part of the human with a bottle of cold beverage. So the red color means high temperature, and the purple or blue color means low temperature. Okay, Stefan-Boltzmann law. The heat current in radiation could be calculated in this way. H equals to A E eta T to power 4. Okay, A is the area of emitting surface. E is emission of surface. And the eta is Stefan-Boltzmann constant. And T is the temperature of the surface. Okay, the radiation and climate change. The energy radiated by the Earth's surface is mostly infrared. Because the Earth has temperature, so it's emitted. It's emitting the infrared, and that type of radiation is kind of transferring the heat to some into the space. However, the CO2 molecules, they can absorb the infrared from the Earth, and that will heat up the CO2, and then the CO2 will emit the infrared radiation back to the Earth. That's why if we look at this figure, while time flying, the temperature is kind of increasing in years on Earth. That's because of the radiation from CO2. Okay, so that's all for the class for the heat and temperature. I will see you in next week. Thank you.